In this video, we will take a look at the conductivity of different substances through the lens of our Conductivity of Matter lab. So we'll start just with a quick review of what electrical conductivity is. And in this class, we are saying that electrical conductivity is the ability of charged particles within a substance to flow. So we'll be using three substances today. So we've simplified the conductivity of matter lab data a little bit. The substances that we are using are sodium chloride, which with the metal and nonmetal make it an ionic compound. We'll be using sugar, which nonmetal, nonmetal, nonmetal make this a covalent compound. And we'll be using aluminum, which by itself is just a metallic substance. We have each of these substances presented in different states of matter. So for the sodium chloride, we have solid, we have liquid or melted, and we have aqueous, which means dissolved in water. We have the same states of matter for our sugar, so solid, liquid or melted, and aqueous, which means dissolved in water. And for the metal, for the aluminum, we have solid and liquid because metals do not dissolve in water. Now, here is the data we collected during our Conductivity of Matter lab. So this data would match your data from that lab. So we found that when we tested solid sodium chloride, it did not conduct electricity. But when we tested melted or aqueous sodium chloride, it did conduct electricity. We found that no matter what state of matter we had, our covalent compounds did not conduct electricity. And we found that of the two states of matter and metals that we tested, they both did conduct electricity. So now we're going to analyze these results through the form of a claim, evidence, and reasoning. So based on the data that we've just gone over, my claim is that for a substance to conduct electricity, it must have free-flowing charged particles. Now this claim comes from both the definition but also the results of our data lab. So my evidence, so using the data, my evidence says that metals conduct electricity in any state that is testable by humans in the lab. What we're saying here is solid or liquid. And that evidence is present in the results of the aluminum test. My other evidence is that ionic compounds conduct electricity when dissolved in water or when melted. So we are going to take a look at the scientific reasoning that will be able to support this evidence or explain this evidence, and this evidence is being used to support this claim. So the first reasoning that we're going to go over involves metals. Now remember, we are talking about electrical conductivity as the free-flowing charged particles within a substance. Metals are pretty straightforward. So we know from our study of metals that they contain a sea of electrons. Sea of electrons is basically just saying that when you put a bunch of metal atoms together, the electrons will delocalize, which means they kind of break free of their parent nucleus and are free to roam through the substance. So metals containing the sea of electrons basically just says that they have charged particles. Remember, electrons have a negative charge and they are a particle. And these charged particles in the form of delocalized electrons are free to flow throughout the substance. This happens in both liquid and solid form. So that's the scientific reasoning that supports the evidence in the data table that showed metals conduct no matter what. And that evidence is what we're using to support our claim. So the free-flowing charged particles in the metal are going to be the electrons in the sea of electrons. Now ionic compounds, when we dissolve them in water, dissociate. So remember, to dissociate means to break apart. When they dissociate, they break apart into their component ions. Remember, ions are just charged particles. Now that these charged particles are no longer stuck together by the attractive forces of opposites attract, they are free to flow within the water. So sodium chloride, when I put it in water, breaks apart into my sodium ion, which is a +1 charge, and my chlorine ion, which is a -1 charge. Now these two ions are floating around freely within the water. So we have free-flowing charged particles. This time, instead of electrons, they are in the form of ions. And they are free-flowing within a substance, so they can carry that charge throughout the substance. So this is for dissolved ionic compounds. For liquid ionic compounds or melted ionic compounds, when we break the bonds that hold the ions together. So what we're saying is when we melt, in this case, by adding enough energy, again, we have now broken them back down into their component ions. So we have sodium ions and we have chlorine ions. They're no longer held together by those opposite attraction charges because we've added too much energy to it. So they just can't stay together anymore. So again, we have a similar result. So when we dissolve our ionic compound, it breaks apart into its ions. We call this dissociation. When we melt sodium chloride, it breaks apart into its ions. Ions are charged particles, and now that we have a liquid substance, we know those particles are free to slide past each other, which is our flowing charged particles. Now remember, before we dissolve it, before we melt it, we have a neutral compound, right? The positive of the sodium is attracted to the negative of the chlorine, and that holds it together to create that neutral compound. That is why solid ionic compounds do not conduct electricity, because they're neutral. They are no longer charged particles because they've come together to create a neutral particle, an ionic compound. Finally, just a quick little snippet about covalent compounds. So they are neutral. A covalent compound or a molecule is neutral, no matter what. They do not contain ions. They're neutral and they're held together by very strong chemical bonds known as covalent bonds. Remember, that's when electrons are shared between two atoms. Those electrons are essentially locked between those two atoms. They can't wander around freely within the molecule, and those electrons being shared holds that whole molecule together. So covalent compounds will be neutral, they will never dissociate, and even when they melt, they remain whole neutral molecules. So hopefully this helps you see how free-flowing charged particles, either ions or electrons, depending on the substance, vary in different substances based on their state of matter. Now, we are specifically talking about aluminum, sodium chloride, and sugar here, but these results can be applied to any metallic, ionic, or covalent substance. So we could use iron, and we would find that iron, instead of aluminum, ends up as the same result. We could use copper 2 chloride instead of sodium chloride, or we could use aluminum sulfate instead of sodium chloride. And no matter what, those ionic compounds will have the same results. We could use glucose instead of sugar, and we would find that we have the same result.